So today, oh, and I have the homeworks for you. Today we're going to study about ATP, which is essentially a small molecule, and it is the universal gas, as in gasoline of the cell. Essentially all cells, individual or many of them, operate by taking some ATP, which is a high energy compound like gasoline, and breaking it down into lower energy compounds. And in that way, it goes into various molecular motors, though in this case, rather than a motor that you have for your car, it goes into little molecular motors that are enzymes that go and take that energy and do something useful with it. And we're going to talk about some amazing facts about ATP, and what we're going to do is talk about how you make ATP. And it's an absolutely amazing rotary motor that operates at near 100% efficiency. Amazing. But it does not violate the second law of thermodynamics. Okay, so with ATP, could you do me a favor back there? Could you shut off the front lights? It's just one of them. Okay, yeah, that's good. Okay, you have ATP, which basically has a handle, which is a ribose. It's ribose as opposed to deoxyribose. So this is like the RNA precursor. It has an adenine with ATCG, that is, it's an A. And it has 3 phosphates. And now the phosphates in general are negatively charged. So what you have is you have 3 oxygen molecules that are negatively charged jammed in there. And that in general takes a lot of energy. So when it has the 3 phosphates, that is, it's ATP, it's full of electrostatic energy. Then what happens is somehow you cut the 3rd phosphate and you form ADP plus, generally it's called inorganic phosphate. And this floats away. So if this floats away from there, there's a lot of energy that is released. If you simply cut it, where does that energy go? Come on, where does the energy go? Into heat. Just random motion. However, if you have it in a special environment, namely you have it in an enzyme, then you can take that energy and do something with it. And that's the entire reason for you being here. Okay, now what we've talked about is this being together or this being separate. So there's an obvious electrostatic potential. And in fact, I will have you calculate that. 2 charges being together. However, that is not all that is going on. What else is happening when you have the 3 charges just right here versus two charges and the one charge over here. So what else is going on? Yeah. The entropy increases. Why does the entropy increase? What does that mean?
The charges are like more spread apart and they have like more disorder and more.
That's right. The charge can be here, or it can be here, or it can be here, and the entropy is different. So actually, you need to account for both factors. And it turns out that when you take into account both factors, you get released of 20 to 25 kT of energy, which it turns out this is units of energy, and this is units of energy. This is force times distance, so that's clearly a unit of energy. In fact, there's about 4 piconewton nanometers per kT. So that's 180 to 100 piconewton nanometers is released, taking into account both the electrostatic and the entropic contributions. That's actually a really useful number. So this is force times the distance. So let's say you have a molecular motor which takes this energy and it produces a certain force and a certain distance. For example, that you can imagine if you want to move an object, and the object in general can't move, so what you do is you put it on a particular type of molecular motor that can apply a certain force over a certain distance. So for example, yes?
In terms of like the energy that's released in ATP, why is there a range? If only one bond gets broken, like what makes the difference?
Okay. I'll get back. That's an excellent question. In fact, it's such a good question that I have it.
Okay.
Thank you. So you have something that has a certain force times a certain distance. And let's say we know that the thing can put out a maximum of, let me just say that 7 piconewtons. This is actually the case. Okay? So how far can it move using the 20 to 25 kT or 80 to 100 piconewton nanometers? So, okay, good. Yeah, you have a minute. Think about it. Talk about it. Yeah. Okay. Good. Okay. Let me just interrupt for a second in case anybody was falling asleep or whatever. The question is, you have a molecular motor that can put out a certain force. In this case, I'm saying, let's say the force is 7 piconewtons. It takes an ATP, then how far can it move that object given that it has taken up 1 ATP? Okay, go ahead. sorry, go back. You have an answer?
Yeah, we have come to an answer.
Okay. What is your answer?
Just divide the power work by 1%.
And so what do you get?
11 to 14.
And so therefore, you can figure out actually what the efficiency of this motor is. And so it's kind of amazing that, and okay, I'll tell you in a second. They don't want to give away everything. Okay. Who has an answer? Okay, and this time we don't allow Greg to talk because he'll make me look really bad. Yes?
Isn't it like 10 to 12 nanometers?
Wait, how do you get that?
By looking at the units. So you have units.
Okay, wait. Come on up. What? You're Dan.
Yeah.
Okay, this is Dan. Hey!
All right, so we looked at the units of energy, which are piconewton nanometers. We saw units before, so we're 7 piconewtons. So we literally just divided it.
Divide what?
80 to 100 piconewton nanometers by the 7 piconewtons.
And then you
You
get,
get units of nanometers.
okay, good.
Which tells you the distance.
Okay, and the distance you get is
Anywhere from like 10 to 13.
10 to 13.
Should
That-
be under 10, yeah.
That's right. Okay. Thank you, Dan. And that's right. So what you have this little molecular motor, so it can move something like, 11 to 13 nanometers. Now, actually, this is in the nanometers, so that's a very small amount. And in fact, we will look in the shortish future as to actually, can we measure that distance? And it turns out that we actually can. And the answer is, in fact, it walks 8.3 nanometers. So in that case, actually, so this times this is what? 56 plus 2, so that's like 58 piconewton nanometers is the actual efficiency. So what is the percent? What percent of the ATP is actually being used to put force and cause a step in this thing? And then what percentage is going to where? So what's the efficiency of this thing? Is, come on, somebody give me the answer.
75%.
Yeah, I don't care about the answer, but how do you get the answer? 58 divided by, 80 to 100. So, this is roughly 75% efficient. I don't know if you're impressed by this, but this is an impressive number. So your motors, this is fairly typical, in your body are converting like 3/4 of the energy of ATP into some mechanical motion. Where does the other 25% go? You guys have already answered. Where does the other 25% go? Come on. You can't hide. So give me the answer. In fact, if you don't know the answer, that's the best of all. Yes?
Heat?
Heat. What is heat? What? Random walk. Basically, heat is just heat. It's causing random things to move in a random direction. So that's right. Now, let's compare this for a moment to like your gasoline engine that is a macromolecule, really macromolecule. What efficiency does your car engine work? That is, it takes a little bit of gas, and in this case, does a force and motion, gets your car moving. So, you know, if you have a Prius, it goes like 60 miles per gallon. So any idea what the efficiency is? 30%, that's right. 30% or 20 to 30%. In contrast, these are like 75, or in fact today I'm going to tell you about one that is essentially 100% efficient. So these molecular motors are really efficient. Okay. Okay. I'm going to have you, by the way, this amount, 20 to 25 kT of energy, is a lot less than a sugar molecule. When you break a sugar molecule, you know, you eat it and then you transform it into ATP. When you do that with a sugar molecule, you do that with a protein, and if you want to get some energy out of it, you convert that into an ATP. They're all much larger than a single ATP. In fact, a single sugar molecule typically gives you 36 molecules of ATP. Okay, so now a long-winded question as long-winded answer, sorry, is why does this have a range? I mean, you can see there's a certain electrostatic energy here versus, you know, when it's over here, and I don't see that being variable. Yes?
Is it depending on like where this ATP is activated? I mean, like, do you think what kind of surrounding or is it near water or like ions, getting the charges out of it somehow? Positive charges around.
Yeah.
No.
It's, oh yes, easy, yes or no. Okay, I give you a 0 or 100%. Yeah, that's basically right. So I'll give you 100%. That is, does it come? Let's imagine you have an ATP and you break it into ADP plus phosphate, and you get a certain amount of energy that's released, and there's nothing, or there's only water around. Now, let's say, in another case, you add salt around. Then the energetics of the reaction will be quite a bit different. And that, in fact, will give you the difference. And in fact, in some cells, there's a real lot of salt, and you get more like the 20 kT, and others you get 25. Yes?
So would it release more or less energy if it was surrounded in salt?
What do you think?
Less.
Why?
I'm like, the whole concept of having this molecule having energy is breaking that OO bond. So the main power of the bond is between those charges. So if you decrease the power of those charges will be time. So definitely your O bond will have less energy, right? Like after breaking, it will be less energy.
Okay, he was saying that with a fair amount of confidence, yeah?
Maybe it's totally wrong. I don't know.
Yeah, yeah, but do you get a 0 or do you get 100?
50? Nothing is 0 and 100, so.
Forget it. Okay, I'll let you think about that. That seems right to me. So how does your body make ATP from ADP plus phosphate? And this is the beginning of this story of the ATP ACE, the enzyme. And basically, the answer is life is powered by batteries. The batteries being across your cell membrane in units of 4 kT of electrical energy. Okay, because you have your cells. And the cell is defined by a cell membrane, which is made of phospholipids. And the lipids, they form because they're very hydrophobic. They want to get away from water. At the other hand, it has a hydrophilic part on the edges. So what that means is this, the membrane, is an excellent insulator. What does that mean? What does that mean? Yes?
It's hard for charges to escape in between the cell and the outside of the cell.
That's right. If you have a charge, it's hard for it to escape, or if you charge here, it's hard to get into it. That's right. So what you do is you somehow start it that there's a little bit more positive ions out here than negative ions over here. The amount is relatively small, the difference, but in fact there's enough of a difference such that there's about negative 100 millivolts on the inside of all your cells. It varies somewhat from like minus 60 or so to minus 120, but basically there's a negative charge on the inside of your cells. And that is what powers everything. Okay. So again, typically about minus 0.1 volts. How much energy is lost by letting a positive ion through? In fact, in the membrane, there are very specialized proteins which act as a gate. In fact, we will study these. And that somehow it lets it through, other times it doesn't. So how much energy is lost by letting a positive ion go through the membrane? Okay, good. You figure it out. I'll give you a minute or so. Yeah, do it in electron volts.
Yeah, I know. Well, it's in, I know it's in. Yeah. What I'm saying is how many will be hydrogen they can turn into make one.
Yeah. Do it in this, and then I'm going to tell you what And you figure out what it is in EV, and you can convert it to KT. Okay. Give me the answer. All of a sudden it becomes very quiet.
7 KT.
This guy's very clever. Okay. So the energy is equal to charge times the voltage. The charge is 1 electron. The voltage is 0.1 volts. So that's equal to 0.1 EV. And KT, it turns out, is a 40th of an EV, or 0.025 EVs. So how many KTs do you get? 4. Wait. But we're saying we get 7. Why do we get 7 instead of 4? Why do we get more?
Oh, it's plus 2 charge.
An electron has plus 2 charge? No, an electron has actually minus 1 charge.
Doesn't like calcium go through this stuff?
You're talking about, would it be for calcium, would it be twice because calcium is 2 plus? Yes, absolutely. But we're talking about singly charged.
Because there's the negative charge inside.
And therefore, what?
It push back on the positive.
That's the energy here. Okay, yeah, he's going for more than 100% this class. Okay, let's give it to him.
Just like randomly shooting out with an idea.
There we go. Okay.
Couldn't be like 2 reasons come to mind. One can be like the insulating property the membrane had, or like meanwhile coming through, there should be like some charges in between, which most probably is not. I'll go for the insulating.
Basically, this is the electrical energy, Q times V. Whenever you think about it, there's some sort of electrical, mechanical, and then there is the entropy, the amount of disorder. And it turns out that you get 3 kT due to an entropy. It's not obvious, exactly why it's 3 kT, but I'll tell you that. Okay? So again, you have to look at delta G rather than delta H or delta E. Okay. Okay, now, can you capture this energy? And also, how do you create the balance in the first place? In terms of capturing this energy, it's involved, you capture it, and you want to convert it into an ATP molecule. You've lost some energy due to the electron flowing, and then you want to gain it and you store it as chemical energy, and then later on you'll use it in a molecular motor or something like that. Do you have a question?
Yeah, I just on the last slide, I was a little bit confused why there were like 2 sets of units that we had. One was just representing the energy of the charge going through the voltage,
Yeah?
which is 0.1 electron volt. But where did the KBT term come from? Is that applying towards anything specifically?
The KB is a unit, and KBT is the temperature of like your body. And so this is the amount, kT is the amount of energy that's in general just sort of floating around. So we want to talk about energy in units of kT, because that gives you a sense of, are you really loading a lot of energy or little energy? So kT is equal to a 40th of an eV. Yeah.
And so that's measured as just like average temperature of a human body.
Yeah. Remember, it actually doesn't matter so much, because T is, what units is T in? Kelvin. So whether you talk about 0 degrees Celsius, that's 273, or 25 degrees Celsius, which is 298, the difference is very small.
And since that's the energy floating around, shouldn't it be like the base energy? So when we get like 0.1 electron volts, we don't get 4 kBT of energy, we get 1 minus 0.025. 0.1 minus 0.025.
No, this is the amount of energy that you've lost, and we're trying to get a sense of how much is that energy compared to kT.
I get it.
Okay. Okay, one question. Yes?
So I don't know if this is like really obvious, but when it says get 7 kBT of free energy, so would that be a positive or a negative delta?
Well, in general, if you have a positive charge going from here and going into here, so a positive charge is going into less negative, so that then you're getting that energy. So in terms of delta G, it would actually be negative, because it will happen spontaneously. Okay. Okay. So what this is saying is, if you're 100% efficient, you're perfectly able to capture this energy, you need about 3 electrons to cross the membrane, because you want 20 to 25 kT, and 3 times about 7 is about equal. So that says 3 electrons is enough to basically drive ATP, if you're 100% efficient. Now remember that. This 3, that's a good number to know. You're going to see that, let's say the enzyme responsible for making ATP from ADP plus phosphate was only 50% efficient. How many electrons would it then take in order to make an ATP? 6. If it's 10%, it'll take, whatever. Okay? So 3. And what we're going to find is that is amazingly that the motor, in this case it turns out to be a rotary motor, operates at near 100% efficiency. So what you have is essentially you have a wheel with 3 prongs. The energy, it opens up, the energy of a plus charge goes here, it rotates the paddle 1/3 of the way, and then another one 2/3, then another one all the way, and every time it does a full rotation, you get from ADP plus phosphate, you get an ATP out. Yes?
If letting in a proton changes how negative the inside of the cell is, wouldn't you have to release the proton and have energy?
That's a very good question in terms of what happens is you have some other system that is creating this minus 0.1 charge, minus 0.1 volts across it. And you have to somehow expand some energy to do that. In fact, where is that energy coming from? Huh? Glucose. It's coming from food that you eat, which is glucose or proteins or whatever. That's right. And it turns out, though, also when you do this, take a positive charge, move it from the outside to the inside, it turns out that the overall change in the charge is actually very small. It's essentially still, it doesn't change the charge hardly at all. Okay. Okay, so this is the model that we have. And where does this actually occur? It turns out it occurs in the mitochondria. Every one of your cells has a mitochondria. And inside the mitochondria is a series of membranes. And it's there that you have the difference, that the H plus goes through the membrane, releasing 7-KT, which then goes into this enzyme, which is called the F1FO ATPase, and actually causes it to rotate. And in fact, after you have 3 rotations, you've managed to take an ADP and a separate phosphate, and you jam them together, forming a new covalent bond, and you get an ATP. So I'm going to show you a model, a cartoon. But before you do that, you just need to understand that there's actually 2 parts to it. There's FO, which is the part that is hydrophobic in the membrane, and then there's F1. And the idea is the proton, or positive charge, is going to go across the membrane. It's going to release some energy. It's going to cause the F1 to rotate. And the F1 corresponds to 3 alphas and 3 betas. And it has a central stalk that is doing sort of the mixing. And it actually goes from here to here to here. Okay, okay. Let's hope that this works. Okay? So here's the F0, here's the F1, and there's a stalk in here. And the idea is this is going to rotate. And over here is the ions that are flowing, in this case, plus charge. And for each one, you're going to have okay, ready? Oh. Hold on. Ah.
The flow of protons down their electrochemical gradient drives a rotor.
I know you want to hear the beginning. Kind of the music kind of gets you in the mood.
ATP synthase is a molecular machine that works like a turbine to convert the energy stored in a proton gradient into chemical energy stored in the bond energy of ATP.
See?
The flow of protons down their electrochemical gradient drives a rotor that lies in the membrane. It is thought that protons flow through an entry open to one side of the membrane and bind to rotor subunits. Only protonated subunits can then rotate into the membrane, away from the static channel assembly. Once the protonated subunits have completed an almost full circle and have returned to the static subunits, an exit channel allows them to leave to the other side of the membrane. In this way, the energy stored in the proton gradient is converted into mechanical rotational energy. The rotational energy is transmitted via a shaft attached to the rotor that penetrates deep into the center of the characteristic lollipop head, the F1 ATPase, which catalyzes the formation of ATP. The F1 ATPase portion of ATP synthase has been crystallized. Its molecular structure shows that the position of the central shaft influences the conformation and arrangement of the surrounding subunits. It is these changes that drive the synthesis of ATP from ADP. In this animated model, different conformational states are lined up as a temporal sequence as they would occur during rotation of the central shaft.
And then ATP is formed, and it's now available.
Like any enzyme, ATP synthase can work in either direction. If the concentration of ATP is high and the proton gradient low, ATP synthase will run in reverse, hydrolyzing ATP as it pumps protons across the membrane. To show the rotation of the central shaft, a short fluorescent actin filament was experimentally attached to it.
This is amazing.
Single filaments attached to single F1 ATPases can be visualized in the microscope. When ATP is added, the filament starts spinning, directly demonstrating the mechanical properties of this remarkable molecular machine.
I wish I had seen this first. This is amazing that I was there at, it turns out it was the Biophysical Society. There was a person, he was a brand new graduate student, well, maybe a couple of years old, and he was Japanese, and so he spoke very limited English. And at that point, we had VCRs and things. And so he gets up there. There's a really packed room because people had heard about this. And he was saying, you know, let me show you how ATPase works or something like that. And he had trouble with his English. So he just said, and he goes and he turns on the video player, and we saw the thing walk like that. He got a standing ovation. It was really something. Okay, so let's...
ATP...
Oh. Okay, so I mentioned how, or it mentioned how the FO and the F1 part has been crystallized, and in fact, here's F1, and in fact the FO has been crystallized also. Then this won a Nobel Prize. Actually, the person who did the first showing that it was a rotary motor did not win a Nobel Prize. I think that was one of the biggest rip-offs going. But there are only 3 people who can win the Nobel Prize and that sort of thing. Anyways. Okay, and wait. Yeah. And there it is going again. What essentially put is a big actin filament, essentially just a rigid rod that it turns out it happens to be fluorescent, so no light, no fluorophore, no light, but if there's a fluorophore, you can see the thing turning around, and then you can do that. And then you can also detect, you can slow it down, and you can see it, yes?
This is a weird question, how in the world did they figure out what it looks like? There are a million parts in that thing,
There are a million parts in it. How do they figure out what it looks like? In some senses, they do X-ray crystallography, where we got more or less an introduction to the X-ray crystallography in the last lecture. So, though in the last lecture, we were dealing with more, the general shape of things. We weren't dealing with an individual crystalline atom or atoms. And nowadays, what you have to do is you do not only have, for example, DNA fibers, but you actually crystallize them. So not only do you see the fibers, but each and individual atom will diffract. And that's ultimately how they did it. And there is, of course, a lot of other work. In particular, he put an actin on top of it and then watched it move. But there was a lot of work that went into this. Okay, and now remember that we still want to see that it is 3 units, 3 electrons that is going to be enough to power 1 ATP. So what he did, this is Kazuo Kinoshita. What he did is he slowed down the amount of ATP, or he added in very little of it, so you could see whether it walked or rotated like this, and then like this, and like this. And he actually found that there are, like this. So this is confirmation that there are exactly 3 steps corresponding to this. And you can see it. And not only that, so he saw it on an individual ATPase with like this rod, this actin rod, but then he actually showed it with a single fluorescent molecule. And the fluorescent molecule has a dipole moment such that the dipole moment is like here or like here. And he showed, in fact, using a single fluorescent dye, maybe there's something funny about the fact that you put a large actin filament on there. So here he showed that it nevertheless worked exactly the same. Okay, and I want to show you one more because this is absolutely amazing how efficient this is. That is, go to the other extreme. Put a huge bead on this, and that one can imagine that there's a lot of force that you need to drive this. And the question is, can it? And no. Yeah. And you're doing it, and nevertheless, it can take this huge bead, and you find, in fact, that it goes around in 3 steps. So what you have yes?
So what was the purpose of the bead experiment? Was it like calculating the amount of force that it creates, or?
Yeah, essentially, well, this is the point, and we'll get to it. What if you scaled this up to the size of U? Each step is made in a time of the order of 0.1 seconds. If F1 is scaled to the size of a person, the person standing at the bottom of the swimming pool would be rotating a rod some 300 meters long at the speed of 120 degrees in 0.1 seconds. The hydrodynamic friction against rotation is absolutely enormous. F1 is really a powerful motor. Okay, so the point is, this little thing, if you scaled it up, 300 meters long, it's rotating around that, which is, I think, absolutely really amazing. So in the case of the bead, that's essentially putting like a 300 meter long actin filament on there, a huge amount of force necessary to turn it. Okay, yes? Okay. How did they attach this enormous rod? And that what they did what they had attached to this shaft, they actually put a stripped avidin over here right on top of it. They end up using a special amino acid. I think in this case, if you're interested, it was using 6 histidines. That a histidine, is one of the amino acids, and it has a special way of attaching it. Yes?
Just the units for ATP concentration, there's like milli, big M. Are they talking about moles?
Yes.
Okay.
In fact, remember, what we tend to do is look at an individual molecule, and so there the units are kT. If you're interested in moles, the units are RT, where R is the universal gas constant, where R is equal to N, which is 6 times 10 to the 23rd, times K. Yes?
You mean that it can only rotate 120 degrees time? If that is not enough, where it rotated by 90 degrees? Or just accumulate the energy until it is enough?
Well, it takes the unit and it rotates things 120 degrees. And it's 0 or 120 degrees. That's it. And in fact, wait. In fact, what he's done is he showed that it doesn't just go in 120 degree increments, which is what I've been emphasizing here, but actually it can go in 30 degrees plus 90 degrees. That is, the ATP cycle, the normal 120 degrees can actually be broken up into a 30 degree and a 90 degree rotation. Okay, we haven't quite gotten to the calculation about 100% efficiency, but nevertheless, I do want to emphasize that we've basically theoretically and experimentally shown that you can basically get out by watching 3 protons move through the membrane. You get out on the order of 21 kT, and that is enough with the transduction efficiency being 100% to getting out in ATP. And okay, last thing, I can't resist. Anybody know what this is? This is a Tesla. It's a really cool car. It's really expensive. My brother owns one. God. Have you ever seen that thing where they step on the gas and everybody goes, whoa, because it has ridiculous acceleration. Anyways, this is essentially 100% efficient of converting electrical energy to mechanical energy. So it's, in that sense, it's very similar to the ATPase. Though the ATPase doesn't cost you $70,000. Okay.